Right, the doors magically closing.
The topology
I
is
think means we got to start.
collection of open sets.
Very happy to see so many of you here, and also people on Zoom. I hope you can all hear us. Let me know. I have my Zoom on in case you don't. Really excited about the candidate we have today, Nivedita Aurora. She's going to be presenting some really cool work. I think lots of you will enjoy it and be very inspired by it, and we'll have some samples that she will pass around and everything. But before that, I just want to give a brief introduction. Nivedita is currently, just started, right?
Yes.
A postdoc at Georgia Tech, actually with Josiah Hester, who I think many of you know, was until recently here close to us at Northwestern University. And before that, she got her PhD like last December or something?
Yes,
Very
January 13th, technically.
Technically like a month ago. And with Georgia Tech as well, with none others than Gregory Avid and Ted Starner. And more exciting than even that credential is really like the work that she's been doing. You're going to see a number of really interesting technical devices, interactive devices that are engineered not just with the principles that good usability and all that, but truly with principles of sustainability, ecological thinking, and how to think of materials in new ways. So I'll just give the floor to her, and I'm excited to hear some discussion at the end as well.
Thank you, Pedro, for an awesome introduction, and I'm really excited to be here today, and thank you all for taking time to come to my talk. So I'll be talking about my journey of building sustainable computational materials. I will start by defining what they are and my motivation behind building them. I will lay down the system design parameters and the progress I have done, taking an example of interactive stickers. I will discuss my cross-disciplinary research process. And finally, I'll lay down a really exciting future research agenda. Okay. So before we move ahead, let's go back 30 years and revisit the vision of ubiquitous computing, which was set by Mark Weiser. So Mark Weiser in the late 1980s, basically that was the era of personal computing, was conjecturing what the technology would look like in the future. And basically he wrote a seminal article in Scientific American in 1991, which was called Computer of the 21st Century. If any of you guys have not read it, I highly recommend you guys to go back and read that. So one of the starting lines of those was, the most profound technologies are those that disappeared. They weave themselves into the fabric of everyday life until they are indistinguishable from it. So basically what he was doing was he was inspiring this new generation in which computing would, is not in that corner desktop, as in everyday objects and surfaces. Or like in the environment around us. And he was saying that it would become so pervasive, so ingrained in our environment, in our everyday daily activities, that we would cease to recognize how prominent it is, or how prominent computing is. So 30 years from that now, we have basically achieved some results of that in terms of Internet of Things, as we have, and you have some sensors around yourself. There are agricultural sensors, there are smartwatches which you're wearing. But the question is, have we really achieved the ubiquity which he was thinking about? So the present day IoT things are not really, everyday objects and surfaces which we use. So think about this sticky note which I have, or the face mask which I'm wearing, or the table, chairs, or the structures which we have around us. So they don't have the computing which we wanted to achieve, or have this, if we take the sentence more literally, which Mark Weiser was initially saying it more metaphorically, we haven't woven computing in the fabric of everyday life. So let me give you some very ambitious examples of some of the things which I have been building, and how computing may be woven into our everyday objects and surfaces. So let me start with an example of a sticky note. So what if this sticky note had, rather than being this, we use this in our everyday life to write text on it and put it on different things to augment with different objects and surfaces information. But rather than that, if this had computational properties, what if it could sense my speech, wirelessly communicate it, but also interact back with me? But at the end of its life cycle, just like the paper, you could tear it apart and throw it in your compost bin. Let me give you another example of a face mask. So imagine having the face mask which I'm wearing, having computational properties that it could measure health data, number of breaths which I have taken, and it can be powered by human breath. But at the end of it, it is upcycled back. The computing by which you have built is easily upcycled back. So let me take another example. So visualize having wireless smoke sensors, and which are basically dropped by a drone into a forest to detect, early localized detection of forest fires. And by the end of their life cycle, once they have done that, disintegrate into the soil itself. So how do we create these computational things? Or better said, how do we create such sustainable computational materials and things in our everyday life today? So let me start by discussing some of the system design parameters which would be required to build such sustainable computational materials. So the first, if you can basically think about, is computing. It requires functionality like sensing, communication, inference, display. But more importantly, what we need to be thinking about is about the form factor. Like material is really important. We need to start thinking about materials by which we are building computing. I talked about sticky notes, I talked about the face mask or sensor being dropped from the, like those would probably are lightweight which need to be dropped. So we need to think about the form factor in which we have been building computing or rethink those things. So they need to be thin, flexible, lightweight, and and finally, and which is one of the really important factors, it needs to be sustainable. So functionality and form factor are only the part of the story. So we will never be able to achieve ubiquitous computing and like weave computing in our everyday objects and surfaces if we are not thinking about sustainability. So let me give more definition of sustainability in terms of 3 system design parameters by taking the example of interactive sticky note. So the first, which all of you could possibly guess is, the first is power, that we need to be building in computation into the interactive sticky note. So do we do that like to having that standalone property which it already had, and to maintain that, it should be self-powered in its operation. Current ways of doing that is being, current IoT devices are requiring batteries require maintenance, they're toxic for the environment. So basically, we need to be thinking about power more seriously. Secondly is cost. So when we think about putting computing in everyday objects and surfaces, we need to be thinking about, can we do it in probably like less than $1 per centimeter square, right? Currently we are at a lot more higher centimeter square. And lastly is basically not the least, but the ecological impact. So how do we think about basically the embodied carbon which we are generating from these, once we have created computing? Firstly, how is it created, but also what happens to it at its end of life cycle. So given these parameters, like we need to be thinking about sustainability, functionality, form factor, but in more of a combined, we need to have a combined focus over all of these things. But how do we build those things, right? Like how can we do this? So let me go back to the basics. So the traditional way of building embedded systems is to, what currently, embedded system designer would do is to go to, Mouser, which is like Amazon or Amazon of components is Mouser, right? You would go take off-the-shelf components, start building circuit systems, add the embedded system algorithm, and create applications. But what we have been doing is we have been building our IoT systems more from functionality first approach. To be able to create interactive stickers, we need to think more from form factor and sustainability first approach. And to do that, we need to start rethinking how we have been building our computing stack. Starting from the materials which we use, thinking about what's the form factor, but also what's the embodied carbon which we are adding in it. But also thinking about what's the fabrication process. The fabrication processes which we use should be simple, democratizable. So, taking the example of sustainable interactive stickers, I have basically developed that more during my PhD thesis, and I have basically right now taken just power, form factor, and cost. That's what I'll mostly be talking about during the talk. But ecological impact is one of the future words, and I'll come back how I'm including all those things together as well. So, taking to explain the projects which I've built for sustainable interactive wireless tickets, I will talk about first the sensing, which is done by a flexible paper microphone which I've built, which is called Saturn, followed by communication, which is done by Mars, which allows you to do like communication in just hundreds of nanowatts. And finally, I'll talk about Venus, which adds display. And given this sensing, communication, and display all together, I will show an application scenario where the interactive stickers which have been built are used as an extended microphone for smart speakers to be able to add, increase users' trust in the microphone's capability. Okay, so let's get started with Saturn. So Saturn is a thin and flexible self-powered microphone. And basically, it consists of two layers. So there is paper, which has copper coated on it, and it has holes in it. Actually, Pedro, if you can pass the prototype along, that would be awesome. And then there is second layer is this plastic, which is a fluoropolymer, which has also copper coated onto it. So basically, what we do is to take the paper side and uncoated side of the plastic and put them all together in a glue dot points. And there's a lot of structural optimizations which I have done, which I'll be also talking about to be able to for this paper microphone to operate. So next I'll start with a demo of the Saturn. Pedro, would you like to come and talk into Saturn? So
Speaking here.
1 second, I'm just gonna transfer.
I'm seeing a Python window.
Yes. Let me make it full screen. Here's my cursor. When I say start, you can speak into it.
Can I speak?
Yeah.
Oh, we need more sustainable materials. I don't know what I should say else. Oh, we need more sustainable material.
Awesome.
I know
Thank
it.
you. Let me do probably one more of it. University of Chicago is awesome. University of Chicago is awesome. Awesome. The demo works. So basically, as you can see, the vibrations which I had from speaking were converted into voltage, and you can see hundreds of millivolts of voltages which would be produced when you're talking from nearby. By the way, I have been carrying the Saturns kind of little bit breaking, but generally it goes on to 1 volt as a general performance which I've seen. Okay, let's go back to our slides. Cursor back and slides back. Okay. So how does this all work? So before I go into more detail, let me introduce this phenomena of triboelectric effect, which you probably are all aware of. So as kids, you probably have seen the science experiment, right? Like you take a comb and you run it through your hair, and then the hair rises up. So what is happening is there is exchange of electrons which is happening between both of them. The comb, which is made up of also fluoropolymer, has the tendency to give off electrons, and your hair has the tendency to accept electrons. So you can arrange these things, every material into this triboelectric series. So the hair is above with the blue region, the fluoropolymers are in the red region. So taking the same concept, you basically what I've done is selection of these two materials which I was talking about. Basically the copper on the paper is one of the layers, and the fluoropolymer, which is this plastic, is the other layer. And because of the triboelectric effect, the copper gets the positive charges and the PTFE gets the negative charges. So what happens is, because of you speaking, because of touching or any kind of mechanical vibration, the charges from the copper goes to the negative layer of the PTFE. And as the layers come together back again, they go back again to the above layer because of the reverse current flow. So with combination of triboelectric effect and electrostatic induction, what you get is what basically we saw in the demo, that as you are speaking, there would be generation of voltages which happens. So Saturn is a self-powered sensor, which means basically the phenomena being sensed provides enough power to do the sensing task as well. And in this case, the sensing task is to be sensing the acoustic vibrations. So let me go a little bit of theory of triboelectric nanogeneration, and we are building the devices, so we need to optimize on its performance. And I always give this example of, for example, when you are, as computer scientists, training neural nets, you train your hyperparameters. Similarly, when you are creating a material device, you have to optimize on the device structures. And to do that, we have this formula, which is like VOC, which is the open circuit voltage. And the sigma is the surface charge density, and xt is the distance between the two plates, which was there. So I have optimized on the surface charge density as well as the xt, which is the distance between them, by different kind of methods, which is, first of all, like paper has holes into them. What is the size of the holes? What is the hole patterns? What is the attachment points by which it needs to be included, put together, the geometry and back support. And I've also optimized on the surface charge density. Basically, this plastic which is there, you can make it rougher by an etching process, and it will have more electrons in it, basically. So let me give you a little bit of, my background is computer science, but I was building these material devices, and one of the things which was very important for me was the reliability, right? And this is why I went ahead and started exploring all these different design parameters. But one of the very interesting things was the center glue dot point, which was found one night trying to, at 3-4 months I was just putting the two layers of Saturn together and ripping them apart, very unsure why the reliability is not happening. So basically what I had to do was to, start understanding how the device works, and more importantly, how the device physics works. So one of the things which happened very magically was that I touched the center point as one day in the center when I was speaking, and then I realized the voltage increased twice, and that was very much seen in the physics simulations as well. That once we did physics simulation, understood how the modal frequencies worked, how the frequency of how the two layers were vibrating, then we were able to understand that having a center glue dot points resulted in more delta x of the two layers effectively over an integral. So that results in much, much better performance. So also much more reliability. So coming to performance characteristics, so generally, for example, an active microphone operates at something like something at 10 dBs, versus Saturn it operates at minus 26 dBs and minus 10 dBs, one which is like the more edged one, which has the surface charge density, like surface process is done, operates at minus 10. And you saw it's easily able to get the sound. It is almost equivalent to basically an active microphone till 5 kilohertz. And 5 kilohertz is a space where you will have 90% of your speech information. So very much you can use it for speech applications. So, okay. So now, having built this self-powered acoustic vibration sensing material, the question was, what do we do with it, right? So Saturn can be used as a sound power harvester. Basically, you have vibrations, there is voltage being generated, you can use it for different applications, or you can put it in a wireless, a self-sustainable system where you're wirelessly communicating the thing. So let me give you first example of a sound power harvester. So here is Saturn, which was being put on a blender, and this was initial one of the prototypes which I was just experimenting with, and I was like, oh, this is really nice. I'm able to charge up a 50 microfarad of, yes please.
Sorry, just a quick question. Does the quality of the material degrade over time? Or is
No, so one of the things is the PTFE is generally, it's also bad for the environment, but at least for initially, this would last for hundreds of years. There is charge which is stored in the material itself. So, but the difference is once I've built Saturn, the Saturn which I was showing from was built approximately 2 years back. And what happens is there is unreliability, which can happen of how the two layers are joined together. So that is why having the glue dot points just has more performance reliable performance characteristics. But what affects Saturn's performance is humidity. Generally, any triboelectric nanogenerator, so Saturn is a type of triboelectric nanogenerator, in a very humid environment, which is like 90 degrees of, for example, humidity, the electrostatic induction which is happening gets affected because so those applications, or you could think about different, for maybe there is an application you have in terms of which requires higher temperature, then different kind of materials would have to be used. Any more questions? Actually, thanks for asking a question. I should have asked for any more questions. Anyone has? Okay, so we can carry forward. So Saturn acts like an acoustic vibration energy harvester. So having done these simple simulations, being able to harvest power, I was like, why not? Pandemic had started to come in, and why not? If we are able to put it in a face mask to be able to do breath-based power harvesting. And there is like very few harvesters which can actually be able to do that. And one of the things Saturn does well is to be able to have high frequency response for the mechanical vibration. It's thin and flexible and its form factor. So we basically published a paper for that. But Saturn is not fully able to power up a microcontroller, but it can definitely extend the battery life of the things. Or you can also imagine that if the system is more intermittent in its computing architecture, then you can think about being able to power it. Okay, so coming back to our main story of interactive stickers. So let's think about how we can build self-sustaining sensing, wireless sensing. So generally, Saturn is an example of a triboelectric nano generator. So the equivalent circuit model which it has is a variable capacitor and variable voltage source. And what happens is you can use both of these properties to be able to wirelessly communicate it. So here is an example of Zeus, which uses changing voltages to be able to communicate the information using analog backscatter. I wouldn't go in detail of that today in this talk, but I'll more of talk about Mars, which is basically uses variable Saturn as a variable capacitor to be able to communicate that information. And the reason I'm more of focusing on Mars is Mars allows you to have multiple tags in the environment to operate together, something like 30-40 altogether in the room environment. And Zeus allows you to have only single tag. But Zeus has very interesting properties of being able to have just only one electronic component, which is this transistor. So you can consider whole of the tag can be printable in the future. Anyway, so let's come back to Mars. Let me show you a demo of Mars before I move forward, where we are being able to use Mars as an extended microphone as I had initially said.
Stickers offer a diverse set of applications and interactions. Leveraging a thin paper microphone connected to Mars, we can enable audio or speech communication. The Mars audio tags can be embedded in a conference brochure and used as an extended microphone for central audio control, allowing the audience to ask questions to the presenter.
What are the power requirements of your prototype?
They can also be used for extending the hearing range of smart home devices to particular areas or appliances. For example, a Mars tag sticker on the refrigerator could allow a user to communicate with a faraway Alexa and update their shopping list.
Alexa, add X to my shopping list.
Alexa, add X to my shopping list.
I've added eggs to your shopping list.
Cool. So you saw how Mars could be used for different applications in the home. So I was showing more of speech-based applications. I have Mars right in my hand, very much a sticker form factor. But Mars can also be used for different other kind of interactions, where you can have this barcode which you are swiping across. You can create these battery-free restaurant menus, or you can have light controls or game controllers which can be built through it. So, but I'm mostly going to focus on the speech part and wireless speech communication part today. So let me give you first example of explain. So Mars uses a technique called frequency modulated backscatter communication. And so backscatter by word means reflection. And let me give you an analog example of what backscatter communication can look like before giving how Mars operates. So think about the sun, right? Like sun has this, like there is this, in old days there used to be something called heliographs. So someone's holding a mirror in their hand and they're taking the sun rays to be able to reflect it back to the target, which is the aeroplane. So what was it, like, what you did not have to have any power at the mirror side. All you had to have was to just, you can just reflect off what the main source of energy which was away from you, which was the sun. Similarly, what you can do is you can have your transmitter, which is like sun. So rather than having light waves, you are having RF waves, which the transmitter is sending. And you have multiple tags in the environment, which are like your mirrors. And what happens is when you have a high frequency wave coming from the transmitter, the tags which are there, they will modulate the information, which is the high frequency wave, based on what the audio which was being sensed, and communicate that back to the receiver, which is acting like a target. So now we have, for example, 4 tags. All these 4 tags are operating at their own frequency band and communicating that information. So how these are able to communicate at their own frequency band is part of the novelty. So the first part of the, people have used backscatter communication for the last 10 years, being able to shift the more power hungry source, so which was the high generation of high frequency radio waves, back onto the infrastructure. So that was one way you can reduce power. But another ways you can reduce power is something which I'll show forward in this, how we have been able to create these interesting different baseband signals with the circuitry. So each of these tags is tuned to a unique frequency, and that is done by an oscillator. So this oscillator consumes sub-microwatts of power, and when I mean by sub-microwatt, so basically something like 2 photodiodes can also power it, rather than generally, especially for audio communication, till now only batteries have been used to be able to communicate that information. So the oscillator is consuming sub-microwatts of power. It's an LC oscillator, and the novelty part is being able to use something called a zero threshold voltage MOSFET as part of the circuitry. So what that does is basically threshold voltage for a transistor is the gate voltage at which the device starts operating. So any basically it switches on. And if you are able to reduce this threshold voltage, which is basically generally being set by a manufacturer, if the voltage threshold reduces, your supply voltage, you can also reduce your supply voltage. So generally, if you know, for example, low power systems would be operating at 1.8 volts or 2.1 volts generally, right? Versus we were able to reduce the average voltage startup voltage to 380 millivolts and the startup power to 500 nanowatts, which is orders of magnitude lower than what even the backscatter based traditional low power communication systems have been able to show. So once we are able to do that, we can have very simple power harvesters to be able to power that. So generally what happens is, how we are able to optimize on cost is that between a power harvester and a general circuitry, there is something called a power management circuitry which is used. And the reason it is used is because the traditional circuitry is operating at 2.1 volts, 1.8 volts, or even mostly 3 volts, right? So you need to have the low hundreds of millivolts where the power harvester is generating and boost it up to that other higher voltages. So because my circuitry is operating at hundreds of millivolts, I do not need the power management circuitry at all to be able to have. So this is how we are able to make the power harvester part really simple. So it can be powered just with 2 photodiodes or with a touch of a finger, as you were seeing in that application. So basically a thermoelectric generator in a room temperature, you can just touch it and it starts powering it. And effectively, the effect of it is just being able to have small form factor and no power management and a lot lesser cost. Coming to the RF front end, basically now that you have built an oscillator, we are able to power it. So oscillator is creating that frequency band. What we can do is to communicate that information. We have created an RF front end which is also passive. So we've been able to select a JFET, which is a transistor, a type of transistor, which will modulate that information and communicate it, but passively. So how does the wireless sensing happen? Is being able to, so we were able to create an oscillator which is an LC oscillator. L is for inductor, C is for capacitor. So you can, this allows you to do inductive sensing and capacitive sensing. So you can basically use an inductive sensor, or we were using a capacitive sensor like Saturn as a variable capacitive sensor to be put into the circuitry to change the frequency band and do the frequency modulation of the baseband frequency which was generated. So this could allow for basically approximately 30 Mars tags to be operating in 10 meters in a monostatic configuration. Generally, when I say monostatic, it's more of like if your target and like basically the transmitter and receiver are at the same place, versus bistatic is when they are at different places. You can double your frequency, like the range of operation when you do that. So that was basically how Mars operates. So when I basically, so anyone has questions? Cool. So when I built Mars, one of the things which I was constantly asked is like, when is the tag communicating its information, right? So current interaction pipeline is, Mars communicates to the receiver, you hear it from example Alexa, or you can have some visual feedback in a public display. But one of the things for more usability, for more privacy, is this need for having a in situ tag, in situ display, which would give you on and off functionality. So having to add displays in basically a system which was already trying to optimize on power, form factor, and cost is a very hard challenge, especially because the type of displays which we have today are operating at 100x more, like 2 orders of more power which is required. So you might have seen, for example, e-ink displays which is used in Kindles. They are supposed to be low power, but they are generally operating at 5 volts. And the activation charge is like 10 millijoules per centimeter square. And then there are electrochromic displays. These electrochromic displays are the ones which you would have seen in aeroplanes. The blue, you've seen that the windows becomes blue, dark blue and light blue when you're traveling. So those are electrochromic displays. And the reason they have used blue, because they're using a material called PEDOT-PSS, which is changing the color when you're providing voltage to it. But how can, and electrochromic displays are really nice because they are able to operate at 1 volt. So when I was trying to decide which kind of display which I could use, so I saw that it could have the activation energy for 1 millijoules per centimeter square. So it was starting to be in the right kind of frame, but still very far away from what I would want, because I was trying to find something which would operate at hundreds of millivolts. So this is why I have built Venus, which operates at something like 370 millivolts joules of, or 370 millivolts can create this on and off functionality. So let me show you a demo of it. So basically you see that being able to provide this square kind of pulse of 370 millivolts plus and minus was able to make it from pink to a clear state. So it operates on the principle of electrochromism, which is basically this principle that when you provide electricity to it, there is a redox reaction which happens, which is redox is reduction and oxidation together, resulting in basically color change. So but another thing is like not just the peak voltages for reduce, the peak, like the power for activation, and the peak voltage, the peak power being used is like less than 10 microwatts for the pixel which was being created. So the device design of Venus is really pretty simple. Basically just like a supercapacitor you would know, or batteries which you would know, it consists of 2 electrodes. One is positive, one another is negative. So let me show it from this. So you can see that this has a pink colored, so there is a working electrode, which is this pink color ECP magenta which is there, and then there is a counter electrode which is this nano ITO which is there. Traditionally how electrochromic devices have been built is that there would be this kind of ink on both the sides. But one of the things which I've done, which was the novel part which I was able to do, was remove the need for the ink which is called conjugate polymer. So there is no need for the ink on the counter electrode. All I have done is to have a coating of something called nano ITO, which lowers down the voltages from 1 volt, which we were able to see, to something like 370 millivolts. And I'll pass this along. Thank you. So the fabrication of Venus display is really simple. Basically, you have a counter electrode, and uses blade coating of nano ITO. There is a working electrode which uses basically an air spray, and you put them all together just like a jelly bean sandwiched all together into this multi-layer structure. So very simple fabrication is used. So this is where things start becoming very interesting, is now that we have been able to build these. Yes, please.
Yeah, can I ask a question about the, what type of electrochromic polymer did you use?
Yes, so we use an ECP magenta. So generally the potential at which it changes is something like 0.5, 0.6. So the novel part was being able to reduce it to 370 millivolts. And the reason that happens is because now the charge balancing layer, which is there, is generally the structure of an electrochromic display is like there would be an ECP magenta, and then there would be something like ECP black, which is also another conjugate polymer is used.
So do you know what's the name of the ECG magenta? I mean the chemical name, chemical structure?
I can give it to you after this talk. How about that? But it's a very big chemical name. So I know it in my head, but it's hard to make it right now. But yeah, that's a great question for like a chemist. I know you. But generally, I think one of the things is like I had to also just to add to a backstory, like if we have a little bit of time. So I was looking for a display, being able to build these, but generally off-the-shelf material, which is speed-on cases, wasn't something which I could use. There are people in chemistry who were working on these conjugate polymers for a long time. So they had built like pink, green, or all rainbow colors. But to them, power wasn't they don't want to reduce it to hundreds of millivolts. So I emailed them, do you have a display which would work at 300 millivolts? And they were like, no. We have something which would work at maybe 500 millivolts and more, but be our guest if you want to try these things out. So this is how a computer scientist goes into a material science or chemistry lab and starts trying to build these things and being able to, let's try to replace what other materials could help in the charge balancing can have lot lower potential for it has vibrancy, but also has a lot lower potential at which it is doing redox reaction. Cool. So once you're able to build these devices, why it becomes powerful is now you can also create these new kind of interactions. Having understood the physics of the device, but also having understood the physics of the harvesters, what you can do is to be able to use, for example, a thermoelectric generator. So if you touch the one side of thermoelectric generator, it produces positive voltage, and if you touch the other side, it generally produces a negative voltage because of Peltier effect. So what we have is this negative voltage and positive. And this is very similar to the square pulse of on and off generation. So what you can effectively do is to think about creation of these very interesting interaction scenarios where you were able to create, when you're touching, you have this pink color go to green. So I put a green colored paper, so because it was going to a clear state, now you can start thinking about new kind of even colors which can be created. And when you reverse it back, then you get back the pink color again. You can put these this low power display into things like, finger powered interactive cards and things like that. You can also control it with photodiodes, where it can go from a default, so from its 3 states, which was basically dark pink, light pink, and clear, it can go from light pink state to a clearless state, which was basically being off, it was pink colored by default, and when it is on, it is clear in its state. So just 2 photodiodes are more than enough for that. So one of the properties which electrochromic displays have is this being semi-bistable in their nature, which means that they are acting like supercapacitors. You can charge, your capacitors, right? You can charge your capacitors, but rather than how much they are charged, you can also see how if you can see your charge with the depth of color, how about that, right? So you can start creating these very interesting properties like optical timers or being, to do voltage level sensing kind of applications. So in summary, like I've basically optimized on functionality, power, and form factor. So functionality of the Saturn being sensing, the Mars being continuous communication, and Venus being of on and off display. For the power part, you saw that I did not want to give any power to the Saturn. There is less than 1 microwatt given to the communication and less than 10 microwatts given to the display. And this is like we are able to start doing audio communication with display in less than 10 microwatts. This is orders of magnitude lower than which has been ever been shown before. In terms of form factor, they all are thin and flexible, and the cost of it is in general in bulk cost. For example, Mars costs $1 or $1.54 with harvesters, but generally the idea is like cost is difficult to quantify in generally. So you can use these everyday materials and simple fabrication techniques which reduces the cost. And we have not used any power management circuitry, so the number of part cost is also low. So let's come back to this application which I started with, how being able to improve the user trust in smart speakers. So currently when you have speakers, what happens is there is a general trust when someone's communicating or not communicating, right? Or like when the speaker is on or off, and what people do is to unplug that from the smart speaker from the thing. What we can do instead is to create something like, let's just create like, I have put all the Mars and Venus circuitry all together in terms of a box structure. And what is there is we have decoupled the microphone functionality from a smart speaker. And what that could allow is to be able to have more trust, building more trust of the user, and more intentional use of the user to be able to use it. So how this box operates is basically there is a hinge, and then there is a physical disconnection which happens when someone closes or opens it. So using this is enabled by more of this idea of using tangible privacy, of being able to, when users are able to physically see that once we open the box, there is a physical connection which happened, and when we close the box, there is physical disconnection which happens. This is really powerful for them to, and there is an intentional action which they did. Plus everything is powered just by light, so that closing and opening the box also powers up the light. So Saturn and Mars are the wireless circuitry part are on the top side, and the photodiodes and the Venus are together on the bottom. So users basically said that being able to have something more of like an extended microphone where they had more perceptual feedback from the display and more intentional powering by this opening and closing the box allowed them to have more trust in being able to control the smart speaker's microphone input. So this is just a small demo where the indicator switches on and switches off. Let me go to my research process actually next. We're a little bit short on time. So my research process is very cross-disciplinary. Basically, I start by thinking about, I'm co-designing between device fabrication, low power systems, and design. So thinking about, there are a lot of times where basically there is changes in the device design is happening because of inspiration from the application or the limitations of the applications, and all the devices are being built to create a particular application. So this is very interestingly and very beautifully things start to happen, and co-designing starts to happen then. I would like to thank a lot of advisors and collaborators which I've had over years, from chemistry, material science to systems to even HCI and privacy, who have really inspired me over time. And going to some of my future research agenda plans for sustainable computational materials. So basically, it's inspired by some deeper understandings which I've had over the time. And I promised this in the starting that I'll talk about more of ecological impact, so let me do that. So one of the things is like being able to have adoption of a more holistic definition for sustainability beyond just energy operation. So thinking more about what are the, from a complete life cycle perspective, starting from manufacturing, operation, and end of life cycle, and thinking more deeply about what is the embodied carbon which is created, what is the ecological impact which is being created. And this was very much echoed by a lot of people when I was able, and I showed them, they were like, okay, what happens to it with the end of life cycle? And NSF has also been trying to say to system researchers, saying there is a recent DCL call which was given to researchers saying that, let's start to think more broadly of sustainability definitions, which takes into account what are the materials which we are using, what are the fabrication processes which we are doing, and what also happens at the end of life cycle. So for that, inspired by that, I'm building biodegradable, flexible microphones these days, basically being able to replace the plastic which I was mentioning about, which was very bad for the environment, with something called basically silk films, and that was being passed around. So you can just extract the cocoons, from the cocoons you can, so thinking about on those lines. So the idea is like, one of the things which we are limited by right now is this, there are the number of components, like the Mauser does not have the right kind of sustainability ratings, it does not have right kind of, when you go, you don't have sustainable devices anymore, like in it right now. So to be able to create this Mauser of sustainable devices is something which I'm very interested in. Secondly, I have built sensing, communication, and displays, but I'm very much interested in building computational circuits. So in the analog computing domain, there is this whole area which has been going on for the last 30-40 years on neuromorphic analog VLSI computing. But what happens when you basically being inspired by the brain, which allows you to do computation at really low power. So, but what happens when you start doing these, analog VLSI circuits in the material forms? For example, if you're calculating a FFT and for doing speech communication, but my material itself is degrading, right? Then my timer is slowing over time because of that. How can you compensate those kind of things in the architecture? Can you compensate for those things in the algorithm level, or can you do those kind of things? And another thing is like, neuromorphic computing is great at doing inference, and intermittent computing is great at doing digital control. So can we build, mix these kind of architectures together, create some new kind of architecture which can be create for the sustainable computational materials. Finally, it's basically thinking about leveraging good design to amplify the impact and adoption of sustainable computational things. So currently, the sustainable computational materials of things which we'll be able to generate probably cannot compete with Internet of Things, but what we can do is to be able to use great design to be able to compensate that, and creating new toolkits and platforms to do that. So I'm very much interested in exploring those kind of avenues. And finally, in terms of application spaces, with each application space, there's a lot of interesting things which can be for health or inbuilt networks, like the infrastructure, smart robotics, or space applications. But for each of these, with the power you're able to harvest, the wireless integration, or the privacy threat models, all of these things change. And with durability changes and all these, like the durability of the application, we need to be able to change the computer architecture as well as the materials and form factor and fabrication of things. With that, I'll come to end of my discussion. It's almost kind of late, but I would like to leave you with this thought of, we have been building our computing stack from a performance first perspective for a very long time, but what if we start thinking about from a more sustainability first perspective? And as research and research community, we need to be thinking and, not just appreciate the performance wins, but also sustainability wins. And that's it. Thank you so much.
If you have any questions, I see already Ben over here.
Hi, so I was wondering, this is very cool, by the way, lots of really neat materials and engineering work. It's super interesting. I guess, and